The Riemann hypothesis is a conjecture in mathematics that deals with the distribution of prime numbers. It was proposed by Bernhard Riemann in 1859, and it is one of the most important unsolved problems in pure mathematics. 1. The Riemann hypothesis is about the zeros of the Riemann zeta function, which is a complex function that relates to the prime numbers in a surprising way. The Riemann zeta function is defined as zeta s equals n equals 1 sigma infinity ns1. For any complex number s that is not equal to 1. This function has zeros at the negative even integers, such as 2, 4, 6, which are called the trivial zeros. It also has zeros in the complex plane with real part between 0 and 1, which are called the non-trivial zeros. The Riemann hypothesis states that the real part of every non-trivial zero of the Riemann zeta function is 21. In other words, the Riemann hypothesis claims that all the non-trivial zeros of the zeta function lie on the vertical line s equals 21 plus it, where t is a real number and I is the imaginary unit. The Riemann hypothesis is important because it has many consequences for the distribution of prime numbers, which are the building blocks of arithmetic. For example, the Riemann hypothesis implies that the prime number theorem, which gives an asymptotic formula for the number of primes less than a given number, is true with the best possible error term. It also implies that the primes are distributed as evenly as possible, without any long gaps or clusters too. The Riemann hypothesis has been verified for the first 10 billion non-trivial zeros of the zeta function, but no one has been able to prove or disprove it for all the zeros. Many mathematicians have tried to find a proof or a counterexample, but so far none has succeeded. The Clay Mathematics Institute has offered a prize of $1 million to anyone who can solve the Riemann hypothesis, or any of the other 6 Millennium Prize problems. 3. The Riemann hypothesis is also related to other fields of mathematics, such as algebraic geometry, number theory, and physics. There are many generalizations and analogues of the Riemann hypothesis, such as the Riemann hypothesis for curves over finite fields, which was proved by André Weil in 1948. The Riemann hypothesis is a fascinating and challenging problem that has captivated the minds of many mathematicians for over a century. It is one of the deepest and most beautiful mysteries of mathematics. Many mathematicians have worked on the Riemann hypothesis, or related problems, in the past and present. Some of the notable names are Bernhard Riemann, who proposed the hypothesis in 1859 and studied the zeta function and its properties. 1. G. H. Hardy, and J. Littlewood, who proved the first results about the infinitude of zeros on the critical line. 1. Selberg, who proved that a positive proportion of zeros lie on the critical line, and also worked on the problem directly. 1. Paul Cohen, who attempted to prove the hypothesis using methods from logic and set theory. 1. Alan Kans, who reformulated the problem using non-commutative geometry. 1. Ken Ono and colleagues, who made recent progress on proving the hypothesis using Jensen polynomials. 2. Yiteng Jiang, who solved a major problem about prime gaps in 2013, and claimed to have solved an analog of the Riemann hypothesis in 20223. There are many more mathematicians who have contributed to the field of analytic number theory and the study of the zeta function, but these are some of the most prominent ones. The Riemann hypothesis remains an open and challenging problem that attracts the interest of many researchers. The Riemann hypothesis is significant for several reasons. First, it is a fundamental problem in mathematics that has been open for more than 160 years, and it has challenged the best minds of many generations. Second, it has deep connections with the theory of prime numbers, which are the building blocks of arithmetic and cryptography. Third, it has implications for other fields of mathematics, such as algebraic geometry, number theory, and physics. Fourth, it is one of the Millennium Prize problems, which offer a $1 million reward for a correct proof or disproof. 1234. The Riemann hypothesis is not only a beautiful and mysterious problem, but also a very important one for the advancement of mathematics and science. Solving it would be a great achievement for human knowledge and creativity. Proving or disproving the Riemann hypothesis is one of the most difficult and important problems in mathematics. There is no simple or general method to do it, and many different approaches have been tried over the years, without success. Some of the main challenges and strategies are: the Riemann zeta function is a very complex and transcendental function, which means that it has no algebraic expression or closed-form solution. It is defined by an infinite series on one half of the complex plane, and by an analytic continuation on the other half. Finding its zeros, or proving that they all lie on a certain line, requires sophisticated tools from analysis, number theory, and algebra 1. The Riemann hypothesis is equivalent to many other statements and conjectures in mathematics, such as the Lindelof hypothesis, the Robin criterion, the Langlands program, and the Selberg trace formula. These equivalences provide different ways to attack the problem, but also show how deep and far-reaching the Riemann hypothesis is. 2345. The Riemann hypothesis is also related to other fields of mathematics and science, such as physics, geometry, logic, and cryptography. Some of these connections suggest that the Riemann hypothesis may have a physical or geometric interpretation, or that it may be solved using methods from quantum mechanics, string theory, or non-commutative geometry. 1. The Riemann hypothesis has been verified for the first 10 billion non-trivial zeros of the zeta function, using computational methods and algorithms. However, this does not prove the hypothesis for all the zeros, since there are infinitely many of them. Moreover, some of the algorithms rely on unproven assumptions or heuristics, which may not be valid for all cases. 1. The Riemann hypothesis is one of the Millennium Prize problems, which offer a prize of $1 million for a correct proof or disproof. This motivates many mathematicians to work on the problem, but also raises the standards and expectations for a valid solution. Any proposed proof or disproof must be rigorous, clear, and convincing, and must withstand the scrutiny and criticism of the mathematical community. These are some of the main aspects of the problem of proving or disproving the Riemann hypothesis. It is not an easy task, and it may take a long time before a definitive answer is found. However, the problem is also very fascinating and rewarding, as it reveals the beauty and mystery of mathematics. The Riemann hypothesis is a conjecture about the zeros of the Riemann zeta function, which is a mathematical function that relates to the distribution of prime numbers. The hypothesis was proposed by Bernhard Riemann in 1859, in a paper titled On the Number of Primes Less Than a Given Magnitude. In this paper, Riemann extended the work of Leonhard Euler and Carl Friedrich Gauss on the zeta function and the prime number theorem, and introduced a complex variable S as the argument of the zeta function. He also defined a region in the complex plane, called the critical strip, where the zeta function is not zero for any real value of S. He then stated that the zeta function has infinitely many zeros in the critical strip, and that all of them have real part equal to a half. This is the statement of the Riemann hypothesis. Riemann did not give a proof of his hypothesis, but he gave some evidence based on his numerical calculations and his intuition. He also mentioned that his hypothesis was very likely to be true, and that it would have important consequences for the theory of prime numbers and other branches of mathematics. However, he did not publish his paper until 1868, after his death, and his hypothesis remained largely unknown until 1896, when Jacques Hardemard and Charles-Jean de la Vallée-Passin independently proved the prime number theorem, using the properties of the zeta function and assuming the Riemann hypothesis. Since then, the Riemann hypothesis has become one of the most famous and challenging problems in mathematics, and has attracted the attention of many mathematicians and scientists. It has also been generalized to other types of zeta functions and L functions, which are related to various fields of mathematics, such as algebraic geometry, number theory, and cryptography. The Riemann hypothesis is one of the Clay Mathematics Institute's Millennium Prize problems, which offers a $1 million reward for anyone who can prove or disprove it. Despite many efforts and partial results, the Riemann hypothesis remains unproven to this day. The zeta function relates to prime numbers in several ways. One of them is the Euler product formula, which expresses the zeta function as an infinite product over all prime numbers. This formula shows that the zeta function encodes the properties of the primes in its values and zeros. Another way is the prime number theorem, which states that the number of primes less than a given number is asymptotically equal to the logarithmic integral of that number. This theorem can be proved using the zeta function and its analytic continuation and functional equation. The Riemann hypothesis, which is one of the most famous and challenging problems in mathematics, is a conjecture about the location of the non-trivial zeros of the zeta function. If true, it would imply a precise estimate for the distribution of prime numbers and many other results in number theory and other fields. Solving the Riemann hypothesis would have profound implications for many areas of mathematics, especially number theory and cryptography. Here are some examples of the consequences of the Riemann hypothesis. It would imply a precise estimate for the distribution of prime numbers and the error term in the prime number theorem 12. It would imply the Lindelof hypothesis, which states that the zeta function grows very slowly on the critical line 12. It would imply the simplicity and non-vanishing of the zeros of the zeta function and its derivatives 12. It would imply the Langlands program, which is a vast web of conjectures that relate number theory, algebraic geometry, representation theory, and harmonic analysis 13. It would imply the validity of many other conjectures in number theory, such as the Dirichlet L-function conjecture, the Artin L-function conjecture, the Birch and Swinnerton-Dyer conjecture, the Sato-Tate conjecture, and the generalized Riemann hypothesis 1, 2, 3. It would have applications to cryptography, as many cryptographic schemes rely on the hardness of factoring large numbers or finding discrete logarithms, which are related to the properties of the zeta function and its zeros 14. These are just some of the consequences of the Riemann hypothesis, but there are many more that are beyond the scope of this chat. Solving the Riemann hypothesis would be a monumental achievement for mathematics and would open up new avenues of research and discovery. That was all. Goodbye.